And we're going to talk about hardware choices for your Cassandra or DataStax enterprise deployments. My name is Kathryn Erickson. I manage a couple of the sales engineering teams for DataStax in the central and federal regions. DataStax, of course you know, we sell the enterprise version of Cassandra. I was previously at Fusion.io, where we sold the enterprise version of the hard drive. And telling people which hardware to use can be a bit of a gray area, hence my gray theme. And although it would be fun to discuss these 50 shades of gray for the next 30 minutes, there's really only 5 shades of gray when discussing the basics of Cassandra performance. And since we only have 30 minutes, and since, to be honest, I really don't know a lot about Java, that leaves us with 4 shades of gray. CPU, which is going to process the instructions for our database. RAM, which is going to hold a working set of our database. It's going to cache our data. And it's going to act as a buffer space for organizing our tables on disk. You have network, which is going to handle the internode and intercluster communication. And then you have storage, which is my favorite. And that's going to be our subsystem that supports and feeds all of these other resources. But what do I know? Well, here's what I know. I've been at DataStax for about 6 months, and thus I know about 6 months worth of Cassandra. I'd like to point out that in my graph you can see I know slightly less about other databases. I have, however, spent a lot of time on server hardware and in file systems. I started down this path at a government contractor. I conducted some cool research, patented some cool stuff. One thing led to another, and eventually we kind of hit a brick wall. We had this database, and queries were taking about 22 minutes. That was for a full table scan. And we replaced the storage with flash, and we went from 22 minutes down to 16 seconds. And I thought, why would anybody ever write good code again when you could just use flash? And so I left, and I went to Fusion.io, and we were going to revolutionize an industry. And in some ways, I think that we did. But then applications called up again, and you didn't need gold standard flash. You just needed good enough flash. And so I figured the next good step would be to go to one of those companies that made good enough flash really be good enough, and that was DataStax. And there are going to be a lot of talks today that discuss the read and write path of Cassandra. If you haven't been to one of those talks, DataStax Academy has a great video tutorial if that's something that you want to learn. But it's based on an LSM tree, and I figured we can at least go over what an LSM tree is and how that works at a very high level. And then when we're talking about resources, you could say, okay, that might be why that impacts that in that way. And this is how that works. You have a write that comes in, and that's written to an in-memory table. I'm going to call that a mem table. More writes come in, and eventually that mem table fills up. When that mem table fills up, I'm going to call it a size 1 table. And because memory is full, I'm going to flush it to disk. Or flush is going to be the term I use for this. Thus, I have a size 1 table on disk. Well, we continue. We begin to write, and memory eventually fills up. Then I have a size 1 table in memory and a size 1 table on disk. And because these are similarly sized, I'm going to compact those together, which means I'm going to sort them and write them to disk as one larger table. It's important to note that not all databases, including Cassandra, are going to compact when memory matches the size on disk, but there's going to be some rule, some trigger that causes compaction to happen. And for my example, it's when memory matches the size on disk. So if I continue this example, I begin writing and memory fills up. I have a size 1 table in memory and a size 2 table on disk. Those aren't similarly sized, so I just flush to disk, and I have a size 2 table and a size 1 table. Stick with me when we're around. I begin writing, and memory fills up. I have a size 1 table on memory and a size 1 table on disk. Because those 2 size 1 tables are the same size, I compact those 2 tables. Thus, I have 2 size 2 tables on disk. So the only logical thing to do is to compact those into a single size 4 table. And at this point, you think, well, that's awesome, but what if your server crashes and you lose everything that was in memory and you haven't written it to disk? Well, you're right. So now we need to add a commit log. The idea of a commit log is that it's a write-only, append-only file, and it's written sequentially, And so if the server goes down and it comes back up, you have this kind of redo log, and you can replay those and add that data back to the database. Now, that's the setup. In the abstract for this talk, I said that there would be this too long didn't read thing at the beginning where I just told you which resources you want. This is that table, and I'm not going to go over it in detail. It's going to be, I'm sure, on the web after this talk. But the idea is, if you're getting started with DataStax or Cassandra, and your workload kind of looks like one of these, well, maybe kind of start with this type of configuration. And if you don't know where, kind of start in the middle. What is good about this slide is the storage recommendations. And just for later, just put in the back of your mind that per server, I'm going to recommend that you use more capacity if you're using SSD than I would if you're using hard drive. That way, when you tell me SSDs are expensive, I can remind you that you're getting more per server. All right. Now, about the network. The only mention of networking is on this slide. And since I started at DataStax, and even up until about 3 days ago, everyone told me we're not saturating 1 gigabit Ethernet. Future-proof if you want with 10 gig, but you only need one. And then Al Toby, our senior performance engineer, comes to me and says, I've got a proof of concept and only 10 servers, and I'm saturating my 1 gig link. Well, he's usually right, and so I would guess that as he spends more time on that, you'll see some performance tuning suggestions that's going to push you more towards a 10 gig network. All right, that's the summary. Now let's get in the weeds. We're actually here to talk about the hardware that's supporting our Cassandra deployment. So let's get right into it. I only have one slide on CPU, and that's because it's pretty simple. The rule is WWPDD, and that stands for what would Puff Daddy do. And Puff Daddy would always throw more cash at the situation, and that's what you should do as well. I asked Al Toby about this as well. He's the guy that I just mentioned. And he said in order of features, he looks at cache, 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 core count followed quickly by megahertz. And so when we're talking about cache, you want to know how much. And I'm going to give you a number of about 20 megabytes, depending on which processor you're using and how much cache you're willing to throw that cache. So you saw in the previous slide, we're somewhere between 4 and 16 cores. You're really going to choose either an 8 or a 12 core system with either 1 or 2 sockets. It's pretty simple. When it comes to NUMA, we're still recommending that you turn it off, turn on memory interleaving, and you will see better performance. Now, when I started to talk about RAM, I only made this one slide. And it was pretty simple. I said, you're going to want to saturate the memory bus, so we're going to use 4 DIMMs per CPU. And we looked and we saw that 8 to 16 gig DIMMs is the sweet spot for your dollars per gigabyte. 32 gig DIMMs are still pretty expensive. And so I thought, with just those 2 things, you can pick which RAM you need for your server. And so what I did was I went to HP's website and I picked the DL380 Gen 9 server. It's one of the most popular servers on the market. And I just stuck with whatever CPU that they recommended in the initial configuration. I clicked the drop-down list for memory, and this is what it gave me. And even I think of myself, as knowing hardware pretty well, I thought it was just really overwhelming. And I walked away from it for a day, and then I came back and I said, well, I have to be able to give some recommendations. And I know you can't see this list very well, but the first column just says HP, that's your vendor. The second column is total capacities, 8 gigs, 16, 32 gigs of RAM total. The third column is the number of modules that it's taking you to get to that capacity. If it's 32 gigs of RAM, it might be 1 32 gig DIMM or 4 8 gig DIMMs. And it's the next column that we're going to look at. It says single rank, dual rank, or quad rank. And if we just know what that is, we can narrow down our RAM choices pretty well. So each DIMM slot in a server has a 64-bit wired connection to the CPU. And a single rank DIMM only has DRAM chips on one side. A dual rank DIMM has DRAM chips on both sides of this module, and thus it can be twice as dense as a single rank DIMM. Now, keep in mind, there's still only one 64-bit pipe to that dual rank DIMM, but each rank can handle 64 bits of data. So technically, you could issue a read to one side of the DIMM and a write to the other while you're waiting for that read to come back on the other side. But you have to remember that these things are happening really, really fast. So you're not getting double the performance. But there is some theoretical, let's call it 7%, performance improvement that you may get from a dual-ring DIMM. Now, a quad-ring DIMM is using the same number of chips, but they're twice as dense. So you have the same number of chips, twice as dense on both sides of the DIMM. Thus, we're able to achieve those higher density 32 gig DIMMs. But they're expensive. Now, let's continue with the example now that we know what that is. I picked an Intel 2630 processor because it's a kind of mid-range Intel processor. It requires DDR4 memory, so a server vendor is only going to show you DDR4 memory. It's 8 cores, and it has 4 memory channels. And that means it has 4 of those 64-bit buses. And when I did this example, I said, well, let's just assume that I have a moderate write workload, and I want a total of 64 gigs of RAM. That means I want 32 gigs per processor. And so from that list, it narrows me down to 4 choices. The 32 gig quad ring module, 2 16 gig dual ring modules, 4 8 gig that are either dual ring or single ring. Well, we know we want to saturate those 4 channels that that processor is giving me. So that narrows me down to 2 choices. At this point, you're good. These 2 processors are going to perform almost the same, and pretty much for Cassandra, they are going to perform the same. And so, since there's some theoretical use case where you may or may not get a couple more percent of performance out of the system, we might as well choose the dual ring DIMMs. So we've gone from this full list down to 2 choices that both make sense. They're similarly priced, and that takes us down to 1 choice for the dual ring DIMMs. And that's an easy way to narrow down your choices. Know your workload, know which processor, populate the DIMMs that match those 2 things. And that gives us a bunch of time to talk about storage. First, we're going to talk about exactly how spinning drives work. Then we're going to talk about exactly how flash works. And then we're going to talk about the storage interfaces that work for both flash and for hard drives, and one that works just for flash. And then we're going to look at some graphs and see if anything that I just told you matters. And since I made the slides, I'm going to tell you in advance it does. So, let's say that we have this thing. And this thing has platters. And those platters have tracks. And on those tracks, you have data that's written. And those tracks spin around. And as those tracks spin around, you have something moving back and forth, reading data as it crosses the tip of that read head. And if I was to ask you right now what that was, a logical guess would be a record player. But it's not. That's how a hard drive works. And in this case, it's a 15,000 RPM hard drive. And you can see in the bottom left, it's kind of your expected performance. And this is real-world performance that we see when testing these drives. About 200 operations per second, average of about 160 megabytes of bandwidth. You might see up to 200. And 5 milliseconds of latency. Now, when I go into a sales meeting and I bring up these numbers, the SAN guy immediately goes, but they've already got all these hard drives. We're just going to short stroke their SAN or these local drives, whatever they have. And this is what they mean by that. The idea of short stroking a drive means that you're only using the outer 10% of the tracks. And the reason you do this is because the read-write head only has to move back a small distance to get that data. And thus, you're reducing your drive capacity by about 90%, and you're increasing your performance by somewhere around 20%. Some might argue more, but that's workload dependent. So let's see what you might be thinking at this point. The obvious question is, did Moore's Law let us down? And the answer is no. Moore's Law has, over the past 20 years, applied to hard drive capacity, and drive capacity has doubled every 18 to 24 months. But it's physics that keeps us from spinning these drives any faster. And if you did the math, you might say, well, technically that drive probably could spin faster. But if it did, it would produce a lot more heat, require a lot more power, and have to be made of very, very strong substance. So, no, Moore's Law did not let us down. The next logical question is, maybe I could just get a bunch of them. And that's kind of true to an extent. You can get more IOPS and more bandwidth, but you're still limited by the physical cable, like a ribbon cable, that's connecting your I/O bus from your processor to your storage device. And you can't scale with latency. Once you get to that lowest point of latency, that's where you are. And then the third question is, well, maybe a sequential write workload wouldn't be so bad. And you're right, it wouldn't be so bad. So that commit log that we talked about earlier, sequentially written, append only, you can put your commit log on disk and it will be happy and it will be fine. Now, the more common questions that you're probably asking are, why does a computer still have moving parts? Isn't there something better? Yes. Your fan would be the last moving part in the server, but we can get rid of the mechanical drives. And then lastly, this is a ridiculous conversation, Flash is cheap now. What we're hearing from a lot of customers, though, is that Flash isn't cheap to them. And so I would say that myself and a few other people have come to DataStax from these storage vendors. If you're being quoted more than about $3 a gig for true enterprise Flash, let us know, because we've got the relationships. We can help you get the best storage. I manage a team of SEs, and they want a solid architecture up front to eliminate a whole set of problems when they're in there trying to help you get the most performance out of your system. We want you on the best storage subsystem that we can help you get. So let's talk about Flash. One advantage, we've already talked about this, no moving parts. So you have better parallelism, better bandwidth, and IOPS. The next is no seek times, which is going to give you low latency. And we talk about that a lot, but we don't really talk a lot about what it means. So imagine that we have this room and this talk in this 30-minute period of time, and instead of me lecturing about hardware choices, you were just to ask questions. And we had one person that was holding a microphone, and somebody in the back raises their hand, we take them the microphone, they ask their question, I answer their question, we bring the microphone back. Somebody else asks the question, we do the same thing, we deliver the mic, we ask the question, we bring it back. In that 30-minute time, we can answer a given number of questions. But imagine then, if when somebody raised their hand, the microphone appeared where they were, and they asked their question, and then the microphone appeared where the next person asked their question. In the same amount of time, we can ask many more questions. It's a simple way to think about why latency matters. Now, because there's no moving parts, you can conclude that there's lower power, and when there's lower power, there's less heat produced and thus less cooling required. And while you might not care about cooling, somebody's paying a bill. Somebody in there cares about cooling. All right. Expected performance can vary greatly. Commodity SSDs on the market will do about 10,000 operations per second. The highest level enterprise drives built for density and performance are doing about 1 million IOPS. They range from 400 megabytes to about 3 gigabytes in bandwidth. And if you remember, I said that a hard drive was about 5 milliseconds latency, and now we're down to under 200 microseconds. It's an order of magnitude difference. But a logical question is, how does Flash work? Oh no, I didn't do the same sound. So when I first go into customer sites, they ask, well, what's the difference between SLC and MLC? With an SLC drive, you have one area on that Flash cell to register a 0 or a 1. With a multi-level cell, which is what we usually recommend to customers, you actually have 2 areas in that cell where you can register either a 0 or a 1. And we're not going to recommend triple level cells yet. We just don't quite have the confidence there. But with a single level cell, a charge anywhere in that space will give you a 0. But as that cell begins to wear, you have a smaller space for which you can register a charge. Well, imagine that exact same amount of wear on a multi-level cell drive. You physically have a smaller amount of space for which to register a charge and to register your 0 or a 1. And that's what causes wear in a flash cell and thus in a flash drive. And the logical question is, does it matter? Well, it used to matter a lot. SSD vendors in the last 3 years have come a long way with grooming and wear leveling algorithms. And we can get the endurance today of an MLC drive that we used to only be able to get out of an SLC drive. And the vendors measure that in 2 ways: drive writes per day and petabytes written. Drive writes per day is the funny one, and I don't particularly like it. It's how many times you can write to your drive over that warranty period. So an enterprise drive usually has a warranty period of 5 years. So you might see an enterprise drive rated as 1 drive write per day over 5 years, but technically that same commodity drive could be a 1-year warranty rated as 5 drive writes per day for a 1-year warranty. And thus, it's not really a great way, because you have to dig in the weeds to really understand what you're buying. A better measure is petabytes written. And that's the total petabytes that you can write to that drive before it wears out. And if you pull up a drive and it says terabytes written, then you might want to find a different drive that's measured in petabytes written. And I told you that I would give you real numbers for these things. And so we always recommend MLC. And the next one is a little iffy. I'm saying 1 drive write per day on a 5-year warranty. But we have customers right now using really crappy commodity drives, and they're not wearing out. Think about how Cassandra works. When a flash manufacturer rates their drives for endurance, they're using a 4K random workload to do that. Well, Cassandra only writes sequentially. Remember, we organize in memory and flush to disk. And when we compact, we read in pieces of those SS tables, those immutable tables on disk, resort and rewrite contiguously to flash. And so, theoretically, it should greatly reduce the write amplification of that drive. Now, we need to do more testing before we can assert that as fact. But we do have the proof points that customers aren't wearing out lesser drives. That being said, if your drive, if your data center is 2 states away, and you have to call somebody in to drive there to replace a drive, maybe go 1 to 3 drive writes per day. If your data center is next door and it's not a big deal to pop drives in and out, and it's convenient, just buy whatever's on the market that's cheap that day. Now, we need to talk about the interfaces for these, whether it's hard drives or disk drives or flash drives. You have SATA, SAS, and PCIe. SATA and SAS doing 0.75 gigabytes up to about 1.5 gigs. I have on here PCIe Gen 2. PCIe Gen 3 drives are out, but at some point it's just bragging. So, since most of the drives are Gen 2 X8, which means 8 lanes of PCIe, I stuck with that measure, which is about 4 gigabytes theoretical limit. Now, does it matter? The answer is yes, it matters a lot. This is a hard drive test of 3 drives, and we're looking at a 15,000 RPM SAS drive that's getting about 6 milliseconds of latency versus 7,200 RPM drives that are getting 8 to 9 milliseconds latency. So they're physically spinning slower, thus the read-write head, moving at the same speed, finds a request a couple milliseconds slower. Now, let's look at the same impact on flash. It looks like the same scale right now, but I'm going to zoom out in just a second. We have PCIe here versus SATA, and we're getting sub 80 microsecond responses for PCIe, and we're getting still under 200 microsecond responses for SATA over flash. Now, the difference in PCIe and SATA, or SAS, is that what PCIe has done is eliminated that disk controller. You're managing with software versus managing with SCSI, SATA, SAS commands. So PCIe when you can, flash all the time, hard drive, commit log. Now, we're looking at this zoomed out a little bit, and if nothing else has told the story, this should do it for you. This is order of magnitude difference in latency. And so if you're writing an application and you have a requirement for, low latency, then SSD is your choice. One thing that people don't always look at that I think is pretty important is consistency of latency. I don't think it's something that's usually reported by vendors. We've done some testing and we have some numbers of some drives that are on the market. But this is the minimum latency at different intervals of time for the same drives that we tested. And you can see that there's the PCIe drive, and I think it's the Samsung drive higher up, that have just actual consistent latency over the life of the test. Now, we have two recommendations here. One is called the SQL Sizer. It's built by Sebastian Estevez, who's one of our senior engineers at DataStax. The idea is that you can put in your create table statement, you can answer some questions about your data, and it's going to help you forecast the size that you need for disk. The other, if you're using DataStax, you're probably familiar with OpsCenter in some way. It has a capacity planner where it just monitors your data growth rate and will help you predict when you're going to need to add more servers and more drives to the system. And in conclusion, CPU, get the most cache that you can for your cache. RAM, we want to stick with 4 DIMMs to saturate the memory bus per CPU. 32 up to 256 gigs. You're not going to usually see more than 128 in Cassandra or DataStax Enterprise System total. And storage, we're going to stick with MLC, SSD. PCIe is still the gold standard for low latency, high bandwidth, and IOPS. And if you need, again, if you need help with pricing there, you just have to let us know. And of course, just to thank everybody that helped with this talk.